All right, last video here for Monday's SI. Just really briefly going to go over some of Gibbs free energy. Still kind of discussion with this. If I learn more, I'll send out what I can find. But again, like I said in the first video, I feel like if she knows that this is something I'm struggling with, I think she's going to hopefully reflect that on the assessment with you all. Okay. Now, there's two ways we can express Gibbs free energy with enthalpy and entropy like we did in class. Okay. There's also another way we can do it up here. Okay. And that pKa values can do a lot of work for us. And we're pretty comfortable now, hopefully more with pKa values. Okay. pKa values and Ka values are inversely related. That is, high Ka value means low pKa, high pKa means low Ka. Okay. So the lower pKa means higher Ka. Now in my equation up here, constant, whatever, blah, blah, blah. It's Gen Chem stuff. We're not worried about it. What we are worried about is this negative sign and our natural log of Ka. Okay. Natural log increases K as we get more positive. It increases not at a linear rate, okay? But notice our natural log function looks like this, okay? And then continually goes upward like that. So notice that Ka values do increase the more we go in that, okay? So if I had for example, very low pKa value, that gives me a higher Ka, which will remain high in the natural log function. This negative sign out here, okay? Now I have a high value that's negative, and Gibbs free energy, something that's negative, is exergonic. Exergonic, okay? So, for example, I have a low pKa, hydrochloric acid. Low pKa means high Ka, okay? My negative sign tells me that I have a negative Gibbs free energy, which is then exergonic, okay? So that's how we relate pKa to Ka, and then Gibbs free energy, and then exergonic or endergonic, okay? This is an example from class, okay? Our acid to begin with, okay? This terminal alkyne at about a pKa of 25, okay? And then we're left with this ammonia compound here, NH3, with a pKa of roughly 35 to 38. Another way of looking at that is that this is 10 to the 10 times more acidic than this, okay? So we could say that this is favored, okay? It's a stronger acid, okay? And it's much more exergonic, energy releasing, okay? Because we have a low pKa, which gives us a higher Ka, and so on and so forth, okay? Now we could also relate this down here to, it's tougher with enthalpy in this case, but entropy, okay? We are starting with two compounds, ending with two compounds, we're not breaking any rings, but, okay, we are making ammonia gas, okay? We're making something that's more random, okay, in a state of matter. I can see her throwing this on the assessment, okay, an energy state, something like maybe H2 or O2 as a product somehow, or ammonia gas, okay? And know when we do that, entropy goes up, okay? We have more randomness because we have something that's a gas rather than a solid or liquid, okay? And as that gets higher, notice delta G gets lower, again, it's exergonic. That's as much as I'm going to say about that, okay? That we have two functions that kind of relate that. Again, I don't think she's going to go super tough on this, on the assessment. And if I learn anything more on it, I'll try and add that over the weekend. Now on to some more familiar stuff and unfamiliar stuff in this video, okay? I expect there's going to be an energy coordinate diagram on there. There's a possibility. She might give something like this and be like, label the energy coordinate diagram. So pause your video, do that. Welcome back. Label the energy coordinate diagram, label the axes, and then also label products, reactants, transition state. Okay, we aren't into intermediate states yet because we're not dealing with like two reactions at the same time. But no, we have energy up here on our vertical axis. I think she had free energy labeled, so energy, free energy, okay. On our y-axis, our x-axis, remember, is not time, it's just reaction progress, or reaction progress is good. That's usually what I use. I think she used something very similar to that, but reaction progress, okay, not exactly time. Okay, reactants, products, transition state. I believe this is a double-crossed arrow. I believe. Check in class notes for that to make sure. But this is the transition state. She might ask to label activation energy. Okay, my activation energy would be this value here. Okay, activation energy. And is this process endergonic or exergonic? This is endergonic. I have a positive delta G. Okay, I'm absorbing energy. Okay, so yeah, there might be an energy coordinate diagram in there. Just have to label. Not too bad of a problem. Okay, last thing I'm going to get into is the reading for Monday. We haven't gone in class yet. I want to introduce it. Okay. Here I have drawn in its most acidic state aspartic acid. Yes. Okay. One of our 20 essential amino acids. Okay. Here I have drawn the pKa values for each of our acids that we're concerned with. We have a carboxylic acid on the top, carboxylic acid on the bottom, and then NH3 plus group here on the left. Now, notice we can actually kind of reason through like, okay, well I have two carboxylic acids, the pKa's are around 4, okay? But why do I have 2.1 and 3.8? Okay? Hopefully now with our cardio rules, we can kind of reason through this. And then I have some inductive effects here, okay, that's kind of maybe decreasing that pKa value. And notice how it's closer to this charge, this group here, than that one, hence the lower pKa possibly. So there's ways we can kind of look at a molecule like that and kind of reason the smaller or larger pKa values. Okay. Here is aspartic acid in its most acidic state. Everything's an acid, everything has its own pKa values here in red. Cool. I have redrawn that same structure here 4 times. Okay, 4 times. This is where we get into 4 times, but also at a different pH level, okay? pH is a measure of H plus concentration, right, okay? Okay, so at a very low pH, I have a lot of H plus in solution to work with. Whereas pH 11, I do not. There's very, very little H plus in my solution, okay? So the way I go about these problems is we have to determine really what's an acid and what's a base at each pH, okay? Our molecule will then be designated a different charge based on that. And whenever we have a neutral charge, that is what's called our zwitterion, okay? So isoelectric effect, we're changing the pH to change the charge in our overall molecule to find our zwitterion. This is basically all we can do with this, okay? All right, so pH, it's very small. That means there's a lot of H plus in solution. My pH here right now is lower than every single pKa I'm given. My pH is lower than every pKa for my acid. That means everything is going to be an acid. Everything is going to have an H on it. There's a lot of H plus in solution, okay? Enough to where everything is going to be protonated, okay? When everything is protonated, this overall molecule has a +1 charge. Notice I have H3 plus here on the left here. So overall, I have a +1 charge. My pH is below that of all my pKa values. Let's move over here, okay? Try this one out, reason through it, okay? My pH is lower than this carboxylic acid and this NH3 plus group, okay? So I'm not gonna change anything, they're gonna remain protonated. What do you think if our pH is higher than a pKa value? We're no longer protonated, and we turn that into a conjugate base. Now our overall charge on this molecule is, I have a minus, I have a plus, 0. This is our zwitterion. If we're asked for the zwitterion, we don't need to keep going. We could stop right here, circle this, ace our assessment, okay? And then go to Tom's SI hours on on Friday, or whatever. Walking hours, okay? Cool. Let's just keep moving here. pH of 8, okay? I have a pH that is lower than our pKa value for our NH3 group, so I don't need to change anything there, okay? Don't need to change anything there. But my pH is higher than my pKa value for both of my carboxylic acids, so what are we gonna do? There's now not enough H plus in solution for these to be protonated. These will turn into bases. And my overall charge will be -1. Hopefully you see a trend here, +1, 0, -1. What do you think our next one's gonna be, okay? -2. My pH is now higher than all my pKa values. Everything is gonna be deprotonated that can be. Deprotonated, deprotonated, deprotonated. So this is now H2, not H3. These lost hydrogens, hence that's where we get our -2 charge, okay? Be comfortable with if pH is lower than pKa, okay? That means it's protonated, okay? If my pH is higher than a pKa, that's when I gotta take that hydrogen off, okay? pH is a measure of H plus concentration. Here there's a lot of H's, everything's protonated. Here there's not a lot of H's, everything's deprotonated, okay? Again, because this is a reading for Monday, she might not go fully ask like a question maybe at this intensity on it. But I think going through this and understanding the concepts, understanding what a zwitterion is, okay, I think is gonna help prepare as well as all the other things we've gone on in these videos. I won't be there Monday, but good luck.